Now that we've stated the second shifting theorem and we've practiced using it with Laplace transforms and inverse Laplace transforms, we're ready to use it to solve differential equations. So remember that the second shifting theorem says that if we have Laplace transform of a function little f equals capital F, then the Laplace transform of a step function ua of t times the function little f of t minus a is equal to the exponential e to the a minus s times capital F of s. So having the step function here causes us to introduce an exponential after we take the Laplace transform. And then equivalently, when we take the inverse Laplace transform of that, the exponential times the capital F function, we get a step function times a little f function shifted by a. So when we use the Laplace method, to solve a non-homogeneous differential equation with a piecewise continuous right-hand side, we end up using the second shifting theorem, because the piecewise continuous function on the right-hand side is going to have these step functions in it. And then when we take Laplace transform of both sides, we're using the second shifting theorem. Then the step functions become exponential functions. Then we solve for capital Y to get something like capital Y equals f of s times, let's say, k1 e to the negative a s plus some other function, capital G of s, times k2 e to the negative bs plus k3 e to the negative cs. So by f of s and g of s here, I mean something, a function of s with no exponentials. And then each one of them is multiplied by one or more exponential functions. Then we probably use partial fractions to find little f of t, which is the inverse Laplace transform of capital F of s, and little g of t, which is the inverse Laplace transform of capital G of s. And then we write little y is inverse Laplace transform of capital Y, and that equals k1 times a shifting function which depends on this exponential, ua of t, little f corresponds to big F, t minus a, plus k2 ub of t. B comes from the second exponential, or exponential next to g of s. G of t minus b, we're shifting the variable in g by the number we saw in the exponential, plus k3 uc of t, g of t minus c. Here we're shifting g, little g, by the number in the exponential there. Now, we needed to take inverse Laplace transforms of the functions without exponential once each. even though g gets multiplied by two different exponential functions, we only need to take its inverse Laplace transform once to get little g. And then we just modify little g once by b, and then again by c for the two exponentials multiplying capital G. Alright, so let's do an example. So let's solve y prime minus y equals f of t, where f of t well, let me put the initial conditions here and I'll write f below. So with y of 0 equals 0, where f of t is the function that's 1 for t between 0 and 1, and 2 minus t for t between 1 and infinity. So we have f of t is 1 times 1 minus u1 of t, that is from 0 to 1, plus 2 minus t times u2 of t, that is starting at 2 and going to infinity. Now if we take Laplace transform of both sides, we have s capital Y minus y of 0 minus capital Y equals, I guess I really should simplify the right hand side. So what do we have? 1 minus u1 of t and this should be a u1 of t here, because starting at 1 we have the second function. So 1 minus u1 of t plus 2 minus t u1 of t. So that equals L of 1 minus 1 u1 of t plus 2 minus t u1 of t. So minus 1 plus 2 is 1. 1 minus t u1 of t. Let me write this as 1 minus t minus 1 u1 of t. Now the Laplace transform of 1 is 1 over s, and the Laplace transform of t minus 1 u1 of t. So this is going to act like a t, and we're going to get e to the minus s times whatever we would get if we took the Laplace transform of t, and that is 1 over s squared. Now the left-hand side, y of 0 is 0. So we just have sy minus 1y. So this is s minus 1y equals that. So we can divide both sides by s minus 1 to solve for capital Y. So y equals 1 over s minus 1 minus e to the negative s 1 over s squared s minus 1. Alright, now these functions without the exponentials are what I called f of s and g of s before. Now this one isn't even getting multiplied by an exponential like that one is, but we can think of it as being multiplied by e to the 0s. So this is one function that we need to take the Laplace, inverse Laplace transform, and this is another one separately. First, we'll do it separately from the exponential first. Now in both cases we're going to need to use partial fractions, although maybe some of us have this one memorized. If we have 1 over a product of two integers that are just 1 apart, let me write 1 over n times n plus 1. That always equals the difference 1 over n minus 1 over n plus 1. So you don't really need to use partial fractions. In this case it would be 1 over s minus 1 minus 1 over s. Because if we get common denominators here, then the fraction on the left is n plus 1 over n times n plus 1. And then the fraction on the right is n over n times n plus 1. And now we can see that if we subtract, we have n plus 1 minus n on top, which is 1 over n times n plus 1. So that means we can write this one immediately as 1 over s minus 1, the smaller number, minus 1 over s, the greater number. But then we need partial fractions to figure out what 1 over s squared s minus 1 is. I don't have that memorized, and I suspect many of you don't either. So let's use partial fractions and figure it out. So 1 over s squared s minus 1 equals a over s plus b over s squared plus c over s minus 1. Now if we clear denominators, this gives us 1 equals a times s minus 1 plus b times s minus 1 plus c times s squared. So if we try, let's say s equals 0, that gives us 1, this disappears, equals b times minus 1, and that disappears, so I guess b is minus 1. And if we try s equals 1, that'll make other things disappear. 1 equals, that disappears, c times 1 squared, so I guess c is 1. And then I guess there's nothing else obvious to plug in, but if we compare coefficients of s squared on both sides, then we've got 0s squared on the left equals as squared on the right. No s squared here plus c. So that means that a is the opposite of whatever c is. So a equals negative 1. So that means we can write this fraction next to e to the minus s as a over s. A is negative 1. Negative 1 over s plus b negative 1 over s squared. And c is positive 1 plus 1 over s minus 1. Alright, so now to take inverse Laplace transforms, we'll look at the parts that don't have any exponentials in them. So they have 1 over s minus 1 minus 1 over s, and this sum of 3 fractions. Let's get rid of the partial fractions up here that we don't need anymore. We'll take the inverse Laplace transforms of these two expressions without the exponential. So the inverse Laplace transform of 1 over s minus 1 minus 1 over s equals, this is an exponential, e to the t, and this is minus 1. And then inverse Laplace transform of minus 1 over s minus 1 over s squared plus 1 over s minus 1 equals minus 1, this is minus t, and this is plus e to the t. Now little y is the inverse Laplace transform of y. So this part we can just copy as it is because it's not being multiplied by an exponential. So we have e to the t minus 1. And then this minus e to the negative s becomes minus u1 of t, because that 1 minus 1 here becomes a shift of 1. And then we take this answer and we plug in t minus 1 wherever there was a t. Minus 1 minus t minus 1 plus e to the t minus 1. And let's see. Minus 1 plus 1 is 0. So that the minus 1 and that minus 1 go away. We have minus t plus e to the t minus 1. And maybe it would look slightly simpler if we multiplied through by minus 1 to write this as e to the t minus 1 plus u1 of t, t minus e to the t minus 1. All right, let's do another example now. So let's solve y double prime plus 2y prime plus 5y equals f of t, with y of 0 and y prime of 0 both equal to 0. Let's let f of t be the function, which is 10 between 0 and 4, negative 10 between 4 and 8, and then 0 after that. So writing this forcing function in terms of step functions, we have 10 from 0 to 4, and then minus 10 from 4 to 8, and then 0 after that. So this is 10 minus 10u4 minus 10u4, and then plus 10u8. So that's 10 minus 20 u4 of t plus 10 u8 of t. Now these step functions here are all being multiplied essentially by 1. When we take the Laplace transform of step function times 1, we're just getting an exponential function, well, times 1 over s, because Laplace transform of 1 is 1 over s. And since 1 doesn't have any t's in it, we don't have to worry about the shifting here. So we've got 10 over s minus 20 over s e to the negative 4s plus 10 over s e to the negative 8s. So that means that y times, we have s squared plus 2s plus 5 here equals, maybe I'll factor out 10 over s. 10 over s 1 minus 2e to the negative 4s plus e to the negative 8s. So that means y equals 10 over s squared plus 2s plus 5 times 1 minus, times s. 10 over s times that times 1 minus 2e to the negative 4s plus e to the negative 8s. Alright, so now we've got one big function of s here, one fraction that has s's in it and no exponentials, times a linear combination of exponentials. So for the moment we just need to focus on the inverse Laplace transform of this. Well, we'll have to use partial fractions on this, and I think we can't factor this, because if we use the quadratic formula that says that s is one of the numbers negative b plus or minus square root of b squared minus 4ac all over 2. So what's inside the square root is negative, so there's no real roots. So we'll have to put this part of the expression in, we'll use partial fractions to make this manageable. So we'll write 10 over s times s squared plus 2s plus 5 equals a over s plus bs plus c over s squared plus 2s plus 5. And then clearing denominators, 10 equals a times s squared plus 2s plus 5 plus bs plus c times s, because this is going to cancel that denominator, bs squared plus cs. That's bs plus c, all of it times s. Now what would be good to plug in? Well, I guess 0. So if we try x equals 0, then on the left hand side we have 10 equals a times 5, 5a plus 0 plus 0. So that tells us that a equals 2. Then if we compare coefficients of s squared on both sides, we have 0 on the left equals a times s squared plus b times s squared. So I guess b has to be the opposite of a. So b equals negative 2. And then if we compare coefficients of s, we have 0s on the left equals 2a s here. No b's times regular s plus c. So if a equals 2, 2a is 4, and that means that c equals negative 4. So y equals, a is 2, 2 over s plus negative 2s plus, minus 4, negative 2s minus 4 over s squared plus 2s plus 5. All of that times 1 minus 2e to the negative 4s plus e to the negative 8s. Now our goal is to take the inverse Laplace transform of this before we use the shifting theorem, I guess 3 times, once for each exponential. So we need to massage this expression a little bit better. The 2 over s is looking good, but the other thing needs to be worked on a little bit till we recognize a sine or a cosine in there. So let's let that expression be capital F of s. Let me factor out a 2. 2 times 1 over s. And maybe I'll factor out a minus 1 here. Minus s plus 2 over s squared plus 2s plus 5. One over s looks great. This on the bottom, I'm thinking looks like s squared plus 2s plus 1, because that would be s plus 1 squared. So s squared plus 2s plus 1 plus 4. So I'm breaking the 5 into 1 plus 4. So this right here is s plus 1 squared. And then on top, I can make that s plus 2 into an s plus 1 plus 1. All right, let me break this into 2 fractions. So we have s plus 1 over s plus 1 squared plus 4. So that piece looks good. And then minus 1 over s plus 1 squared plus 4. All right, that's looking close, although I kind of wish I had a 2 in the numerator. So let me multiply by 2 and by 1/2 at the same time. So minus, I'm going to say 1/2 and change that into a 2. And then I can take the inverse Laplace transform of this and that. So I'm all good. So then f of t is the inverse Laplace transform of capital F of S, which is, so we've got 1 here. Then this part looks like cosine of 2t, but times e to the negative t by the first shifting theorem. And then this looks like sine of 2t, but times e to the negative t by the first shifting theorem, and we've got a coefficient of minus 1/2. So minus 1/2 e to the negative t sine of 2t. Now, little y equals the inverse Laplace transform of capital Y, which is the inverse Laplace transform of f of s times this linear combination of exponentials, 1 minus 2e to the negative 4s plus e to the negative 8s. So we don't have any exponential multiplying f of s the first time, so we can copy this exactly as it is. 2 times 1 minus e to the negative t cosine 2t minus 1/2 e to the negative t sine 2t. Then the e to the negative 4 here means we get minus 2 times all of this with t minus 4 plugged in. So 2 times 1 minus e to the negative t minus 4 cosine of 2 t minus 4 minus 1/2 e to the minus t minus 4 sine 2t minus 4. And then this third exponential is going to mean that we copy that whole expression again with t minus 8 substituted for t. So plus 2, 1 minus e to the minus t minus 8 cosine of 2 t minus 8 minus 1/2 e to the negative t minus 8 sine 2 t minus 8. So again, we took this expression 3 times, one for each of the exponentials. 1 means we used it exactly as it is. E to the minus 4s means we plugged in t minus 4 everywhere there was a t, and e to the minus 8s means we plugged in t minus 8 everywhere there was a t. And in case it's helpful, let me rewrite this. It doesn't simplify much more than that, but let me rewrite this as, so what we did is we got f of t minus t minus 2u4 of t f of t minus 4, so that means plugging in t minus 4 for all the t's there, and then plus u8 of t f of t minus 8. And actually I forgot to plug in, forgot my u4 and my u8 here, so this is really minus 4 u4 of t times this, and this is plus tu 8 of t. Because all of those exponentials on the right hand side have now become step functions, u4 and u8. So this is the final answer. The end.